in this lecture we will be solving a few problems which span the entire course in some sense. So, this will be in a way this is a gist of the entire course. So, the first problem is from the first module. So, here the problem I will read it out. Let the width of the channel be 10 micrometer, it is a long channel device, and length be 1 micrometer, and with long channel behavior at room temperature, what we would like to calculate for this given source, drain, voltages, and what is the total silicon charge Q silicon, depletion charge, and for near the source edge and near the drain edge. So, how do we do that? So, we had discussed this F function which relates the total charge in this silicon region with the electric field, and using that we had obtained the relationship between gate voltage, total silicon charge, and also gate voltage and inversion charge. So, this we will use here. So, the F function, its value we will calculate. So, now we need to substitute the value of V. What is V at the edge of the source? At the edge of the source, V is 0.5 or 0 volts, because the source is grounded here, assume grounded. So, this is 0 volts. So, here at the edge of the source it will be 0 volts V, the channel potential. And at the edge of drain, because you have increased the drain voltage to 0.5 volts, this local channel potential would be 0.5 volts there. So, this adds to the surface potential. And how do you calculate the surface potential? Using this. And what is the value of VFB? Here you can take VFB to be 0, because we have not discussed any VFB here. So, you get the value of surface potential using this expression. This is surface potential plus the increase in electric, this accounts for the increase in electric field because of the charge, silicon charge, which is mostly in near threshold and subthreshold operation, which is mostly because of the depletion charge. Relatively an inversion charge is smaller. So, that is this expression you use, and from this you calculate the F function, from this you calculate chi s. So, this becomes a quadratic equation and you can get the value of chi s. So, there will be two values of chi s, one of them will be physically meaningful, other one would come out to be negative. So, you can ignore that. Then you calculate the F function by using chi equal to chi s. This is obtained from 1, okay. And V is at the source edge and at the drain edge, the value of V would be different, like we have mentioned here. So, this is the total silicon charge then, and this is depletion charge, where you calculate the body effect factor like this. This NB is 10 to the power 18 per centimeter cube. Depletion capacitance, after this depletion capacitance is simple, you just substitute into this. At the edge of drain, you will have the local channel potential also added into it. So, in this first part is that you estimate the leakage current of the NAND gate, 2 input NAND gate, for VA being 0 and VA being VDD. VB is always 0. So, this is a NAND gate which will not switch because of the change in VA. When VA is 0, there is some leakage current flowing through the series stack. VV is anyway 0, so V out is VDD. So, there is some leakage current which is flowing. This is 0, this is also 0, this is at VDD, near VDD. Since there is some leakage current flowing, there will be finite VDS for this transistor, lower transistor. So, Vx is greater than 0 in this case. So, since Vx is greater than 0, this would have a negative VGS, which makes the leakage current extremely small. So, how would you now do this leakage current through a device? For example, the device B is given by this expression where rho is the value with which the N MOSFETs are sized. Okay. Rho is the value in the one of the approaches Pedram's paper that we had, Pedram's group's paper that we had discussed in the course. So, what is this rho? Rho is the size of the N MOSFETs, these N MOSFETs relative to the size of the N MOSFETs in the inverter, factor by which you should increase the size of these N MOSFETs. But here let us take rho to be 1, which does not matter because rho would be equal for both the NMOS devices. So, even if you take it to be 1, whatever you calculate, it can be scaled, the leakage current. The leakage current would get changed only by a factor rho. So, that is why taking it 1 is not an issue. Width, this is, and then you have, so this is for the transistor B. What is the gate voltage? VG equal to 0. So, therefore, it is VGS. So, this is VGS therefore. So, this is the VGS of transistor A minus X, and this is the VDS of transistor A. Minus Vx is the VBS, body to source voltage of transistor A. So, this is transistor A's current. Now, if you want to write transistor B's current, in this case, what is the value of VGS? 0 minus VTHN plus lambda Vx. Vx is the value of VDS minus bodies to source voltage is 0. This is VGS of transistor A, B, VDS of transistor B. This is VBS of transistor B. Okay. Now, equate IA and IB, because equal current would be flowing in steady state through both of them, and that is the leakage current for case 1, for the problem 1. For problem 2, this was done in our lectures, and where B was lower transistor was off and upper transistor was having a voltage VDD. So, in that case, since the current has to pass through the lower transistor also, Vx will again be larger than 0, and the value of Vx can be calculated. We had done this in our lecture, this formula. The value of Vx can be calculated from using this expression, and then again equate the currents. So, we can write down the current expressions there. This was obtained by equating currents. So, that is going to be a trivial task. For this case, IA is Wn ION exponential. Again, the expression looks similar. VGS is different now. So, it is VDD minus Vx. This is Vgs minus Vthn plus lambda VDD minus Vx minus gamma Vx divided by NVT. IB is given by the same expression. IB, the expression does not change. So, equate I and IB and we get the value of leakage current. So, once you know Vx, it is easy to calculate. Leakage current is IB itself in steady state. You know Vx and it is easy to. Now, to obtain VDD optimum and for a given frequency, what is the value of Vth to be adjusted. So, that we have discussed this expression in the course of the lecture. So, here what is the logic depth? This path is off. So, logic depth here is 1, 2, 3, 4, these 4 are in our path, and so solve this, substitute values of VDD optimum instead of this symbol and solve this. So, we keep on changing the value of VDD optimum, at one of those values you will get this value. So, it is simply some numerical technique can be used, or you can use trial and error. That will give you a solution. Trial and error itself would give a solution. For VDD optimum, now you have, since this does not depend on threshold voltage, we had discussed in the course that the desired VTH can be obtained separately for a given frequency. So, this is for minimizing energy, but then frequency can change. So, for a given frequency, how do we estimate? So, this VDD desire, we had derived this in the course. So, using this you get this value. So, this is regarding the metastability detector that we had. So, to design the metastability detector in a Razor flip flop. So, in both the paths we had differently sized inverter, in one there was this INV N and in another one we had this INV P. So, how do we obtain this? Just by equating currents and realizing that V out and V in both are VINV. So, equating currents, we have these two expressions. Now, both the devices are in saturation. Because at the inversion threshold, both would have a VGS which is VDS, which is much larger than VT, thermal voltage. So, we are just equating these two currents, PMOS and NMOS currents, and replacing V in by V in and V out wherever we see them by Vi and V. So, in this all the transistors are minimum sized. This inverter has the same input capacitance as this inverter, because all of them are minimum sized. So, what is to be done? So, here for the second part we require to know what is the delay that is to be kept between clock and delayed clock. So, why is the delay kept in the first place? So, it is kept because you may not be charging IM sufficiently, and therefore, with clock delay this shadow latch would get charged properly. So, for that the delay should be equal to the delay of this transmission gate, inverter followed by transmission gate. So, if the setup time is actually the delay of this inverter followed by transmission gate, if that is violated and if IM is not sufficiently charged, then shadow latch should take over. So, if the data to clock offset is smaller than the delay from here till here, from this input to IM, then we should keep an offset between clock and delayed clock of that much. So, into IM delay this should be equal to the offset between clock and delayed clock. So, how much is this delay? That is the question. So, we are estimating that using RC delay. So, we are taking the resistance R of the inverter I1 followed by the transmission gate T1. Once we obtain that, then the RC time constant would determine the delay. So, how do we obtain this effective or average resistance? For that, we first calculate the voltage of node X. How do we do that? Suppose this is discharging, the value of node X would be sufficiently high such that it is much larger than the thermal voltage. So, all the transistors would be operating in subthreshold saturation. So, the IP of transmission gate plus IN of transmission gate would be equal to IN while discharging of inverter I1. Okay. So, how do we calculate these currents? Now, this is for part A. This would be exponential VGS. So, the node IM is at higher potential. So, that is the source and clock is 0. So, clock bar is 0, sorry, this clock bar is VDD and clock is 0. Okay, for that condition we take we calculate this. So, because that is when the transmission gate is conducting. So, we want to get the delay while it is conducting. So, VGS is VIM, which we assume to be VDD here, minus VTH minus lambda VDS, VDD minus or lambda magnitude of VDS, VDD minus Vx minus gamma body factor VSB, which is 0 here for the P MOSFET, by NVT plus ION, VGS for the N MOSFET in the transmission gate is VDD minus VTHN minus lambda into VDS, which is, because the node voltage of IM we are taking it to be VDD here to estimate the current. So, it is VDD minus Vx again plus body factor plus the contribution of body factor, which is VSB. So, now that is Vx, okay, divided by NVT. Now, this is equal to IN of the inverter's NMOS. So, the inverter's NMOS, it is ION into, so since all the transistors are minimum size, the width factors would cancel. ION exponential. Now, what is its VGS? VDD minus VTHN plus lambda VDS, which is Vx, minus body effect, which is 0, body voltage NVT. So, this we equate, so and we obtain Vx. Once we obtain Vx, the discharging current is the current of the N MOSFET of I1, of inverter I1, which is the same as this. Here you take the width into account, which is minimum width, and you get the value of this discharging current. What is the resistance? This discharging current is the current of the entire inverter followed by transmission gate. So, the and we are assuming the voltage of node IM to be VDD. So, resistance R would then be VDD divided by IN of inverter I1. Now, let us look at the part B of the problem. So, what is the delay from in to IM? So, let us take the capacitance to be C, input capacitance of this inverter. So, the delay is R, we have already estimated, R into C into natural logarithm of 2. So, this should be the offset between clock and the delayed clock. So, this we know how we obtained this. This is just by saying that VDD by 2 for 50% delay is equal to V out is equal to VDD exponential minus T by C. So, where this T is again replaced by delay. So, in this question we want to estimate the total power consumption of this part, ignoring the inverters. So, what is the state of the circuit? So, voltage VA, as we had discussed in the lectures, is a high value. So, M5 is off. Since M5 is off, you get a voltage here which is VDDH minus magnitude VTHP. So, for that calculate the current through M3. So, how much is that? I naught P width of this exponential VGS minus VTH, which is 0. So, VGS is VDDH minus VTHP minus VTHP plus VDS lambda VDS, which is again VTHP, magnitude VTHP, because here you have a fall of VTHP. This is the value of Vg minus source voltage. So, minus VTHP plus lambda into VDS, which is again magnitude of VDS, which is again VTHP, and body voltage, which we are assuming 0 here, divided by NVT. This is the current IM3. Now, for IM4, it is the voltage VA, which is its VDS. VGS minus VTH is the same. So, first we need to equate the currents of IM4 and IM2. IM4 equal to its VGS is the same as IM3 for IM4. So, with that we estimate the value of V A. So, how much is that? So, IM4, for IM4 we assume it to have the same width as IM3, M4 and M3 widths are same. So, the current would be IOP exponential. Now, VGS minus VTH is 0 as for M3, as we have seen for M3. So, we have, and body voltage we can assume 0, since you will have a contact given to VDDH, a well contact. So, this will be exponential lambda VDDH minus VA. This is the VDS divided by NVT. This is equal to IM2, which is ION exponential VGS, which is 0, because VDDL is V in is VDDL. So, here you will have 0 VDDL. So, VGS is 0 minus VTHN minus plus lambda VDS, which is VA, minus we can assume that substrate contact is there and therefore, body voltage is 0 divided by NVT. From this obtain the value of VA. Once you have obtained it, then this itself is the leakage current. So, add for I leakage into VDDH is equal to power consumption. So, which is VDDH into IM3 plus IM2. You can also use IM4, both would have the same leakage current. Now, let us move to the next question. So, in this 60 SRAM cell, which is operating at VDD, metastability point lies at 0.5 VDD. Now, we are trying to reduce the supply voltage of the cell, that is, we are trying to reduce the VDD of the cell. Bit lines are at the older VDD and word line would also operate at the older VDD. So, reduced VDD is only for the cell. This is one of the techniques that we had discussed in our lectures for increasing write margin. So, we want to calculate the pulse width, how much the pulse width has to be changed for a successful write operation if VDD of the cell is lower to 0.8 times VDD of the word line and bit line, okay, 0.8 times. So, we have some simple values given here to simplify the problem. Here, to take the worst case margins, we assume that this does not change from 0 and this only the voltage value of VQ changes. So, we assume that VQ has arrived at the metastable point, and once it has arrived at the metastable point, so then the switching can take place, flipping can take place, and that is what is required for write. So, there we assume what is we calculate what is the current, and that current would discharge this. So, now for higher VDD what is that current and for lower VDD what is that current. The ratio of those two currents would determine how long the, so we are assuming that current to be the current during the pulse, which is not true, the current would change. So, how does this operation take place? Initially it is at VDD, so it would discharge with a large current, but once the voltage value of Q reduces, it would discharge with a smaller currents. So, we are estimating the current at the metastable point, so that it is the lowest current that we are using for calculating our pulse width. So, with that current we will be comparing for the nominal voltage and lower cell voltage operation, and for both these cases, and ratio of those two currents we will say that the discharging current has now reduced by this much. So, pulse width has to be increased by the same value, because we are assuming that to be the worst case constant current to be flowing during the pulse, world line pulse. So, what is our approach here? We IM2 has the highest value when VQ equal to VDD. During flipping, VQ has the value of the metastability point. Metastability point, okay. IM2 is smaller for this value we take this worst case value to be the discharging current during the word line pulse. Another thing that we do is we look at the VTC. Since these inverters, back to back connected inverters M3, M1 and M6, M4 are completely alike in this problem. So, we draw this 45-degree line and then we draw the VTC. Suppose this is for M3, M4, M1, M3 nominal voltage. This is for M4, M6 for nominal voltage. For lower voltage, as we had discussed in the course, this would again come on the 45-degree line. So, we reduce this by 80%. This will be for M1, M3, 0.8 VDD. As we had discussed, if these in back to back connected inverters are similar, then all the metastability points would lie on the 45-degree line. So, to be very accurate, we can actually estimate both the metastability points by reducing VDD. We already know the formula for VINV. So, we can calculate VINV, inversion threshold, for 80% VDD. That can be done using the formula that we had discussed. In this lecture, we had discussed it previously for the skewed inverters, problem 3. So, the same formula can be used and you can actually estimate the value of VINV for 80% VDD again. So, how would you solve the problem? So, first estimate the value of current IM3. So, from these values get this, and so it is now proportional to 0.5 VDD, and Im2 similarly is proportional to 0.6 VDD for nominal voltage. Now, VDD is changed. Using a similar approach, we would find that Im3 is now proportional to this and Im2 is proportional to this. So, here we have taken VINV at the metastability point to be VDD by 2, which is 0.4 VDD. Lower VDD. So, here VINV is VDD by 2. Because M2 is operating in saturation, its current would not change much. So, we need to take the ratio of IM3 how much has it reduced? That would, by the same ratio you can reduce the pulse width. So, that much smaller pulse width can now sustain flip of the basic memory cell. So, as we have already discussed, the VDD of the cell is changed and VDD of WL is the older VDD, earlier VDD, VDD of BL is also earlier. So, to write 0, bit line is at 0 and bit line complement is at the older VDD, earlier VDD. So, what would happen because of this? Substituting these values, IM3 for VDD cell being equal to VDD, here VDD cell for these two VDDs VDD cell is equal to 0.8 VDD. So, here, so for VDD cell being VDD, substituting these values, we get IM3 to be proportional to 0.5 VDD, IM2 to be proportional to 0.6 VDD. If now VDD cell is reduced to 0.8 VDD and VDD of the word line and bit line is the same as the older VDD, in that case inversion threshold would change a little from VDD by 2, old VDD by 2 to VDD cell by 2. So, in that case this IM3 would be, so here you would have in the worst case, so when the device flips, when the inverter flips, you should have V inversion here. So, if you have V inversion here which is 0.4 volts and this is, we are assuming for the worst case the currents this to be still at 0. So, this is at V inversion, so it has maximum current P MOSFET. Now, because its drop VDS is largest possible before flipping. After V inversion, we are assuming that it will flip. So, after this Q goes below V inversion, we are assuming that it flips. So, here it has the maximum current before flipping and that maximum current is proportional to 0.3 VDD. So, the device is operating, we are assuming it to be operating in saturation because this is VDD by 2 around 0.4 volts, 0.8 minus 0.4 volts, which is larger than the typical velocity saturation related VDSAT of the device. So, we assume it to be in saturation and we get this subthreshold saturation and we get this value of the current through M3. What about M2? This is again in subthreshold saturation because this is at 0.8 VDD and this is 0. So, for that the current comes out to be this much, proportional to this. Now, you can observe that the rate of discharge of this node Q would be the difference between IM3 and IM2 because IM2 discharges this, IM3 charges this node Q. So, rate of discharge of Q would be the difference between the IM2 minus IM3. Now, word line pulse width would be inversely therefore proportional inversely to IM2 minus IM3. It should be kept inversely proportional to this, so that the discharge happens within a certain time. So, word line pulse width, so we can see that IM2 minus IM3 increases by around 3 times when VDD is reduced to 0.8 VDD for the cell, VDD cell. So, therefore, word line pulse width can be reduced by 1 by 3 by a factor of 1 by 3 when you reduce the cell supply voltage by 0.8 times. So, in this lecture we have discussed problems pertaining to almost all the areas which were covered in the course. So, thank you.